is as part of this review. So the first question that you had from your quiz on Friday was a question about this other algorithm called the Toom-Cook algorithm. It doesn't matter how it works. It's a divide and conquer strategy for multiplying two n-digit numbers, similar to Karatsuba multiplication that we did cover. A particular variation of this algorithm splits the two integers into three parts, each 1/3 the size of the original. The recursion, however, requires 5 recursive multiplications. Set up a recursion for the algorithm and provide an asymptotic characterization for this. So this is just plug and chug. You need to set up a recursion here. If m sub n is the number of multiplications required to multiply two n-digit numbers together, well then we can recursively do that 5 times on numbers that are 1/3 the size, right? So n divided by 3. And then there's no recursive cost here whatsoever, okay? It's very similar to Karatsuba, only the base conditions have actual multiplications. So this is just an application of the master theorem. You just have to identify the constant coefficients here, the parameters here. A is 5, B is 3, and then C or K or D or whatever it is that we do, that this function right here is order n to the what? Well, if it's constant, if it's 0, then it's order n to the 0, right? It's just constant. So now you just need to look at A versus B to the D. Well, 5 versus 3 to the 0, and you come up with that it's strictly greater than. Okay, and I think that is from memory case 3. Right? Question mark, which it means that m sub n, this is why it's open book, open note, open computer. You don't have to memorize those kind of things. You can go right to your notes on the master theorem, look it up, case 3, great. Let's go ahead and plug and chug now. And I think that that's going to be n to the log base b, which is 3, of 5. Right? Then you take out your calculators and you calculate this, that this is going to be order of n to the 1 point something something something. And then you say, well, is it better than or worse than Karatsuba multiplication? You just look at the exponent here. Does anybody have a value for log base 3 of 5? 1 point what? 5.9? Okay, that's good enough for me. What was Karatsuba's multiplication? You remember? I think it was 3 multiplications on numbers that were half as big with 0. So it's going to be 3 versus 2 to the 0. It's going to be the same case, but it's going to end up as being log base 2 of 3. I have no idea what that is. Log base 2 of 3 is going to be? 1.4, 1.5, okay. Again, this is why it's open book, open note, open computer. You can look these things up. Or you can put them in a cheat sheet if you want to. All right, consider the binary search tree in figure 1. For each node, indicate its balance factor. So we're not actually inserting anything. We're not actually deleting anything. We just want to know what the balance factor is. The balance factor of any leaf with no left child, no right child, that's easy. That's going to be 0 across the board for all of these leaves, right? What about 9? It's the height of the left subtree, height of 1, oh sorry, height of, is that it? All right. The height of, sorry, this one. The height of this, of 9, the height of the left subtree, well, the left subtree is just a seed, so its height is 0, minus the height of an empty subtree is going to be 0 minus -1, so that's going to be 1. What about the height of 15? It's going to be the height of the left subtree, which is 1, minus the height of the right subtree, which is -1. So that's going to end up being 2. What about the height of 20? 1, 2, minus the height of an empty subtree is 1, so it's going to end up being 3. Let's do these over here. Well, this is a completely balanced tree, perfectly balanced, so it's going to have a balance factor of 0. What about this one? 1 is the height of its left subtree. -1 is the height of its right subtree. So 1 minus -1 is going to end up being 2. This one is going to be 0 minus 1, 2. So it's negative 2. And what about this one right here? The height of this tree is 1, 2, 3. The height of this subtree is 1, 2, 3. So it ends up being balanced at the root. This is not a real AVL tree, of course. It's already unbalanced in several different places. You would never end up with an AVL tree like this anyway. It was just to ask you to see if you knew what the balance factors were and how to compute them. On the back, unfortunate. Consider inserting keys into an initially empty AVL tree in the following order: 30, 20, 10, 40, and 50. We'll do it right here with new paper. There we go. So let's insert 30, 20, 10, 40, and 50 in that order into an AVL tree and show any rotations that result. So if I insert 30 into an initial tree, well, of course, if it's empty, then it's just one element. Likewise, in the second step here, when I insert 20, it's going to end up being the left subchild of 30. The balance factors here are going to be 0 and 0 minus 1, so negative 1. It's balanced it's as balanced as it can be. But when I insert 10, that ends up being a left child. So there's 3. So there's what kind of a rotation are we going to do to fix this? A right rotation. And it ends up being 20, 30, and 10. We next enter 40. Let's make sure that this is actually balanced and that we don't actually do any rotations here. This is a balance factor of 0, 0. What about this one? Negative 1 minus 0 is going to be negative 1, so it's balanced. Remember, AVL trees, you're allowed to have 0, 1, or negative 1. What about this one? It's going to be 0 minus 1, 1. So it's going to end up being negative 1. Negative means that it is unbalanced slightly to the right. Positive means that it's unbalanced to the left. So no rotations after this. The next one, after we insert 40, 50, it's going to end up being the right child of this. So let's go ahead and go back down here. 20, 10, 30, 40, and 50. Let's quickly just do some balance factors here. This is 0. What's this going to be? Negative 1 minus 0, so negative 1, unbalanced to the right. What's this one going to be? Negative 1 minus 1, so it's negative 2. And that's where we do our rotation. What kind of rotation are we going to do here? A left rotation. This is a right rotation. And when we do that, we end up with 20 and 10 are still there, 40, 30, and 50. There. And then that was it, into an initially empty AVL tree. Consider entering the same keys into a 2-3 tree. And I said rotations here. I meant any promotions, right? So let's go ahead and start with 30. And I do. This is somewhat clean here, so I'll go ahead and do it this way. What happens when we insert 20? Insertions always happen in a leaf in a 2-3 tree. So this was called a 2-node. It has one key and either 0 or 2 children. So it becomes a 3-node where it's got 2 keys. It's got 20 and 30. Okay? What happens when we insert 10? Temporarily, it's over full. Right? It's got 3 keys. That's a 4-node. So what we need to do is promote the middle element. And we end up with a regular old binary search tree here, all with 2 nodes. Okay? What about 40 and 50? What happens then? 40 is greater than 20, so it comes over here. It's always inserted as a leaf. So we end up with 20, 30, and 40 being a new 3-node. And we're good to go here. Right? Everything is at the same level. That 2-node, there was room. It could become a 3-node. What happens to 50? 50 is greater than 20, so it comes down here and gets inserted as, temporarily, it becomes 30, 40, 50. But it's full. So what do? We promote 40 up. Is there room for it to live? Yep, there's plenty of real estate in there. So 20, 40. That becomes a 2-node. A 3-node. A 3-node always has 3 children. Two keys, and thus 3 children. So what happens to the remaining of 10, 30, and 40? They all become 2 nodes. Sorry, 10, 30, and 50. They all become 2 nodes. And that was Friday's quiz. Okay? Any questions so far? Or if you have questions that you want to take a look at or ask before we get into, this is from last year, summer 2018. No? Okay. Then, these are all one-sided, so it's all going to be okay here. Let G be an undirected graph. An independent set in G is a subset of vertices, called I, such that no 2 vertices in I are connected. In other words, if you look at all the vertices in this independent set, there's no edge between them. Right? They're completely disconnected. Design an algorithm that, given a graph G and a positive integer k, less than or equal to v, the size of v, determines if G has an independent set of size k. Provide pseudocode and provide an analysis of your algorithm. So I'm going to go ahead and write the pseudocode, and then we're going to, again, you can exploit pseudocode to generate combinatorial objects. The combinatorial objects that we're going to want to generate are subsets of size k. Clearly label your input, though, first. Our input is going to be a graph, G equals v comma e, and an integer, k, less than or equal to the size of the vertex set. Our output will be, and you can also put on, trivially, a single vertex is going to be vacuously an independent set. So you could say that k is at least 2, right? We're going to output true if G has an independent set of size k and false otherwise. Okay? So, what kind of combinatorial objects am I going to generate? Subsets of size k. We know how to do that because I showed you an algorithm for doing that. Right? There's also another algorithm called that I thought I would try to demonstrate this year, but I didn't. I think it was Grover's algorithm. No, that doesn't sound right. So it started with a G, but it's a way that you can quickly generate subsets using bit strings and bit string manipulations. But unfortunately, it only works if you've got a fixed size bit string and it actually works in your particular programming language. But don't worry about it. Maybe I'll show it next year or something. All we need to do is a simple for loop for each subset I of the vertex set of size k. Now before we go on, remind me, how many of them are there? How many possible subsets are there of a set of size, we'll call it n, right? N is the size of the vertex set, that's the convention. How many subsets are there of size k? 2. What combinatorial object am I going to be looking at here? It's in the name itself, combinatorial. Combinations are, there are going to be n choose k of them, right? And we'll come back with that with our analysis. For each subset of size k, we need to verify whether or not it's an independent set, right? So I will set a flag, right? Is independent set is, right? We'll assume that it's true until we find reason not to believe that it's true by finding an edge. Right? So for each pair of vertices, let's call it x and y in I. I is our independent set that we think is an independent set, and we're trying to verify that. If x and y is an edge, then we've found reason to believe that it is not an independent set because two vertices in this set are connected. And the requirement is that they are not connected. Okay? So if we find that they are connected, then is independent set, we can set that to false. And if it is an independent set, then we can stop and we can output true. You found an independent set of size k. Right? Otherwise, if you get through every single possible subset of size k and none of them are an independent set, then you can output false. Now there are n choose k, which is going to be order n to the k, subsets that you have to check. For each pair of vertices in this independent set, well, how many are there in here? How many are, this is an independent set of size k, so k choose 2 if you wanted to look at it that way. This is simply going to be order k squared, right? And you can call this your elementary operation. We know that this actually, from Friday, we know that this actually has a different behavior depending on if it's an adjacency list versus an adjacency matrix. But that's not important to this algorithm because that's just a subroutine. We'll go ahead and call this our elementary operation. And so we end up doing this many times this many times this many edge checks, basically. Right? So altogether, if you want to go through the 5-step process, the input is going to be our graph, G. Our input size is going to be the size of the vertex set. Our elementary operation, edge checks, and line, 1, 2, 3, 4, line 4. Label the rest 5, 6, 7, 8. There we go. 4, how many times is it done with respect to the input size? Well, it's this times this, so it's going to be, if you want to put them all together here, that is n choose k times k choose 2 times 1 and 5. This is simply going to be order k squared n to the k, if you want to get real technical. Okay? Now k, if you consider it to be a constant, then this looks like it is polynomial, right? That's just a constant sitting out front. This is just a constant power, and so this is going to be polynomial in n. Nope. K can run from 0. It can run from 2 up to n, right? So in the worst case scenario, you could make it so that you're looking for independent sets of size n divided by 2. And if you've got sets of n, size n divided by 2, how many are there? Well, that's n to the n divided by 2, and that's certainly going to be exponential. This is an NP-complete problem. Right? You're not solving this in polynomial time. But brute force is good enough for this, this midterm right here. This is very similar to quiz 1 here. A little bit more detail. Suppose that we have an algorithm. It's just a black box algorithm. We don't know how it works. Who cares? That takes a graph k and g and an integer k, right? And returns true if g contains a cycle of length k, false otherwise. Further, suppose that it runs in order n to the 4th running time. That is definitely not correct because this is another NP-complete problem and there's no known polynomial time algorithm, but we're just saying suppose that it runs in this time. Use this algorithm as a subroutine to solve the following problems. Give good pseudocode and full analysis. A, what we're going to do is, given a graph G, determine if it's a tree or not. Remind me, what is a tree? It's an acyclic graph. So if I can ask questions of the form, are there any cycles of length 3? Are there any cycles of length 4? Are there any cycles of length 5? If the answer to any of those questions is yes, then is it a tree? Nope, because it has a cycle. If the answer to all of those questions is no, then guess what? It's a tree. So all I need to do is, you should write out input, output here. But I'm going to go ahead and write is tree. And we'll come back and set that initialization there. And we're going to test for k running from 3 up to, what's the longest cycle that you can have? Say that you've got 4 vertices. What's the longest cycle that you can have? 1, 2, 3, and then you've got to go back to the original, so 4. So I'll go all the way up to n, where n is the size of the vertex set. That's just always a convention. Right? If A on G and K is true, here's a pet peeve of mine. It should be a pet peeve of everybody. I see this way too often in actual code. Let me go ahead and write what here. Let me write it in pencil here. Is equal to true. Should you ever do that in real code? No. It's good enough to simply just have this. This is either going to be true or false. Why should you why should you ask an additional question as, is it equal to true? Is it equal to false? There's no programming language that I know of that requires you to do equality testing on a Boolean value. So don't do that. Just do it like this. If it's true, then what can you tell me? It found a cycle of length k. What's your conclusion now? What? It's not a tree. So output, false. If you want to, document it. Not a tree. And I don't think that we're going to need the flag variable at this point, right? If you get through this entire thing and you never output or return false, then there's no cycle of length 3, 4. There's no cycle of length 5. There's no cycle of length 6. There's no cycle of length n. What do you output? True. Right? Now, if this costs you n to the 4th, and you're doing it order n times, then altogether, what is it? N to the 5th. Okay? You can give a full analysis if you want. Or, you should, if it asks you to. But that's the idea right there. B, given a graph G, determine if G contains a Hamiltonian cycle or not. What is a Hamiltonian cycle? It's a cycle that visits every vertex exactly once. So what's its length going to be? N. All you need to do is output A, G, and N. That's it. Well, if it runs in order n for the 4th time, then this is going to run in order n to the 4th time, right? And that's it. Okay? Of course, there's no such algorithm, right? There's no such algorithm known. That would imply, if there were, that would imply EP is equal to NP, right? This is an NP complete problem. These are Turing reductions, by the way, and we'll get to that at the last part of the course. Gomer. I always use Gomer because nobody in real life has ever named Gomer. And Gomer is a classic idiot character. If you know TV, Gomer Pyle. It's from the Andy Griffith show, I think. Yeah. Way before all of our times, by the way, before my time too. They're talking about black and white TV way back in the day. Gomer has studied Strawson's matrix multiplication and thinks that he has come up with several brilliant new insightful breakthroughs. His first claim is that he's come up with an identity that if we split the matrix into 9 parts instead, so kind of like this, right? We're splitting a matrix up into 9 parts, each 1/3 the original size, then the number of multiplications can be reduced to 6. Assuming he's correct, is this really an improvement? Briefly justify your answer. So if you look at the number of multiplications, this is similar to your quiz from Friday, you can reduce the number of matrix multiplications down to 6 recursively on things that are 1/3 the size, and then no non-recursive cost here. So A is going to be 6, B is going to be 3, and D or K or whatever it is going to be 0. So 6 versus 3 to the 0. Well, 6 is clearly greater, so I think that this is case 3 applies. And we've got that it is order n to the log base b, which is 3, log base b of a, which is equal to log base 3 of 6 is going to be what? Log base 3 of 6. Help me out. Order n to the what? 2 point, or is it 2 point? No, it'd be like 1 point what? 6.3? Okay. Is it an improvement over Strawson's? What was Strawson's? Strawson's was like n to the 2 point something something, right? So yes, it's an improvement. Yes, it is better than an order n to the 2 point something 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 from Strawson's. All right? Assuming that it's correct, right? B is A. Now he claims that he is able to use Strawson's original split, in other words, 4 submatrices, each size 1/2 the size. But he's able to reduce the number of recursive multiplications to just 3. Right? Do you remember how many multiplications there were in Strawson's? 7, right? So instead of 7 as a number of recursive calls, it's going to be 3. And they're all 1/2 the size because it's the original split. Okay? So A here is 3, B is 2, and D or C or whatever it is 0. Sorry, yeah, there we go. So 3 versus 2 to the 0. Well, we still have case 3, right? Case 3 is going to be order n to the log base 2 of 3. And what's that going to be? Again, this is just master theorem application. That's going to be 1 point something something something. What is it? Anybody? Well, I'll let you fill that in. Open book, open note, open computer, open Wolfram Alpha, right? 1.5 what? 5.8. Okay, good enough for me. All right, both of these, that's even better than this, right? So, is his idea reasonable? Are either of these ideas reasonable? How big is the matrix that you're, how big are the 2 matrices that you're trying to multiply together? They're n by n matrices, so how many entries do you have? N squared. This is sublinear, right? In other words, Gomer is claiming that you can do matrix multiplication without even looking at all the input. Is it reasonable? No, right? And that's all we were looking for, right? That for the vast majority of algorithms, unless you've got some structure that you can exploit, there's a trivial lower bound of linear because you have to at least look at the input. Right? That looks familiar. I just reused the tree. Consider the tree in figure 1. Is it a valid 2-3 tree? If so, prove it by providing a sequence of inserts into an initially empty tree that would result in the tree. Right? So, what could we do? Where is it? Like I said, does that look familiar? Oh, not 100% familiar, but the exact same structure here. So, since it's not exact, let's go ahead and try to figure it out. Let's see. How many permutations would you have to go through if you wanted to do this brute force, if you wanted to check every single possibility? There's 1, 2, 3, 4, 5 keys. So how many permutations are there of 5 keys? 5 factorial, so 120. I think a lot of them would end up with the same thing. So let's just go ahead and try it. What if we did it in order? Let's try this one. 5, 10, 15, 20, and 25. All right. Let's go ahead and insert these in this order. So this is 5, and then 10. All right. Oops, what is 2, 3 tree? Sorry. So 5, and then 10, it becomes a 3 node. Then we insert 15, and what happens? 5, 10, 15. 10 gets promoted, and we have 10, 5, and 15. Then we insert 20. It gets inserted over here, and that becomes 10, 15, and 20. And then we insert 25. Oh, 5 is over here. And then we insert 25, and that's over full temporarily. Which one do we promote up? 20. And so we've got 10 and 20. And 5, 15, and 25. There we go. The hard question would be, come up with a sequence that would not result in that. I don't know what it would be off the top of my head. But going in order, that'll get you there. There are many, many answers. There are 120 permutations. Many of them would satisfy it. Okay? Let T be a 2-3 tree, a 2-3-4 tree, which is a generalization of a 2-3 tree that can have nodes with 1, 2, or 3 keys, and thus 2, 3, or 4 children. Let H be the height of T, or you can use D as the depth of T. What is the minimum number of nodes that T could have? This is kind of a red herring question, in that it doesn't matter that it's a 2-3 tree, 2-3-4 tree. It doesn't matter that it's a 2-3 tree. If you want to minimize the number of nodes, then what would you end up doing? You would end up making everything into a 2 node, in other words, a regular binary tree, or full binary tree. Right? But because it's a 2-3 tree, a 2-3-4 tree, you're forced to put every node at every level all the way up till the end of the level. Now, does anybody remember, again, open book, open note, open computer, does anybody remember the how many nodes are in a tree of depth D, or I guess in this case H? The height of is going to be the same. How many nodes are here? 1, 2, 4, ... At height H, it's going to be 2 to the H, right? And what's the summation of all these things? 2 to the H plus 1 minus 1 of 2 to the I running from 0 up to H. Yep, exactly. All right? Good. Here's a min heap. Right? Verify that it's a min heap. This is less than both of its children. This is less than both of its children. Less, less, less. And it's full at every level except for the last one, and it's full and to the left. Okay? Show the operations necessary to insert 4. I'm going to go ahead and go with a pencil here. Where would this end up being to insert 4? Where would I end up inserting 4? Do I start at the top like I do with binary search trees with heaps? Nope. I end up at the bottom, the next available spot, and I put 4 right here. Right? Now what happens to 4? Is it a min heap, by the way? Nope, because 10 is greater than its child, so we end up swapping. 4 ends up here. Is it a heap now? And 10 ends up down here. Is it a heap now? Nope, because it's less than its parent. So we end up swapping. So 1, insert. 2, swap. 3, swap. And it's less than 3, so we end up only doing 2 swaps. 3 comparisons, because we compare it here to swap, compare it here to swap, and then we end up with doing one more comparison to see that we should stop the swapping process. Right? And you can rewrite all that if you want to. Right? I just did it on the figure here. Starting over from the original heap, show the necessary operations to remove the minimum element. So we don't have 4 here anymore. So let me go ahead and redraw their heap over here. 3, 5, 25, 30, 40, 17, and 10, 23, and 20. There's the original. So step 1, save 3 off. So we've taken it off so that we can restore it later, or return it, okay? What's the second step? We need to make sure that the fullness property is preserved. So what do we put up here? Do we put one of its children? Nope. We promote the last element up there, 20. Promote 20 to the root. And the fullness property is now satisfied. But is the heap property? Nope. It is greater than one of its children, but not the other child. So which one do we swap it with? The minimum, right? So swap. 20 is now here, and 5 is now up here. 20 is here. We swap it with the minimum, and 20 ends up down here, and 10 ends up here. Okay? Then you heapify, swap with its minimum child until fixed. Fix heap, whatever you want to call it. Prove or disprove. Swapping any 2 siblings, 2 children of the same parent, always results in a valid min heap. Prove or disprove. Do you think that that's true or false? False. Why? Okay, on that one. 5 and 25. What'll happen? Is it full to the left anymore? Nope, and now it's full to the right. So disprove and just explain that. All right? You'll end up with a big gap in your array-based implementation. Okay. It was it's kind of a red herring kind of question in that if you just think about the keys, of course you could, yeah, if you just thought about the keys in isolation, 30, 40, they're both less than its parents, so yeah, what's the big deal? It's not a binary search tree where that wouldn't work, but it won't work because of the fullness property. So careful. Insert the following keys into an initially empty 2-3 tree. Okay. 8. Then we've got 2, 8. Then we insert 9, and we temporarily end up with 2, 8, 9. And 8 gets promoted to 8, 2, and 9. Then we insert 10. It's greater than 8. There's plenty of real estate there to be. So what was it, 9 and 10? All right. Then we insert 4. 4 is less than 8, and there's plenty of real estate there. 2 and 4 over there. 8, 9, and 10. What about 3, though? What happens with 3? 3 comes down here to 8. It's less, so it gets inserted here temporarily, but it's too full, so we promote 3 up. Promote. And we end up with 3, 8 as the root. Those got split up into 2 nodes. This one stayed the same. There we go. 12 now. So 12 is greater than 8, so it comes over here. And now this is full. So 10 gets promoted up. And temporarily, we've got 3, 8, 10. And 4 children of 9, 12, 4, and 2. We can't have that. So as the next step, 8 gets promoted, and we've got 3, 10, and now you've got those 4 children perfectly fit for all these, 9 and 12. Great. The last one we insert is 5. 5 is less than 8. 5 is greater than 3. And we insert into a leaf, so we end up with 8, 3, 10, 2, 4, and 5 as the only 3 node, and 9 and 12. And circle them all. Okay. Same exact thing with numbers though. Insert it into an AVL tree and then show the rotations. So 8, 2, then 9, right? Do we have to do any rotations yet after inserting the first 3? Nope, it's perfectly balanced. So what about 10? It's going to end up being its right child of 9. Now, we could rebalance this. We could do a couple of rotations, but is it going to help? What are the balance factors here? 0, -1 minus 0, so -1. 0 minus 1, so -1. And over here, it's of course going to be 0. It's as balanced as it's going to be with 4 keys. Okay? What about 4? 4 gets inserted as the right child of 2. That's not going to change any of the balance factors except for 2 and its parent. So this is 0. This becomes -1 minus 0, so this becomes -1. And this one now becomes 0. It's even more balanced than it was before. Right? That's 10, 4. What about 3? What ends up happening? Where do you insert 3? Less than 8, greater than 2, less than 4. So we're over here now. Let me go ahead and rewrite this. And let's go ahead and put in the balance factors. There we go. So this is going to be 0. These are unchanged because we didn't do anything. 0, -1. Up here, this is going to be 1, 2, -1, but this doesn't get changed until we consider lower down here because this is where we inserted this. This is going to be 0 minus -1, so this is going to be +1. What about this? This is -1 minus 1. What happened? -2. That's too unbalanced. What kind of a rotation are we going to do now? It's unbalanced to the right, and then its right child is unbalanced to the left, so we need to do a right, then left rotation. Right? Just in the reverse. Right? It's unbalanced right, then left, so we need to go left, then right. And when we do that, 3 comes over here and it gets rebalanced. We have 8. 3 is the new root. 4 got pushed over, and 2 got pushed over here. And then 9 and 10. The new balance factors here are 0, 0, 0, 0. Right? These are unchanged, -1 and 0. Next is 12. That gets inserted right, right, right. 12. Now what are the balance factors here? 0. This is unbalanced to the right, but only slightly. -1 minus 0. This is unbalanced, -1 minus 1, so this is unbalanced completely to the right. So what kind of, it's unbalanced to the right, its right child is unbalanced to the right, so we do a left rotation. And when we do that, we end up with a full binary search tree. 10, 9, 12. The other side is unchanged. 2 and 4. Okay? And then the last one, 5, is not going to matter because there's no way that you can rebalance that. But let's put in the balance factors here. Every leaf is going to have a balance factor of 0. This one will be -1 minus 0, so -1. This one will have 0 minus 1, so -1. This one will be 0 because it's perfectly balanced. What about the root? The left subtree has a height of 1, 2. The right subtree has a height of 1, so 2 minus 1 will be 1. Okay? It's slightly unbalanced to the left. That's because we just inserted 5 over here. Okay? That was one midterm. We breezed through it in 45 minutes. You should be able to do it in an hour and a half. Right. Okay. This is, I'll let you choose what you want to do. This is another graph algorithm, just generate combinatorial objects to do a brute force kind of thing. That might be interesting. There's that's a 0-1 knapsack again, but it's kind of like the second problem we just did. They're all having the same flavor, just different problems. There's Strawson's again with a bunch of inputs, and what would the approximate running time be, or etc. Cycle graph, give an algorithm to determine if a graph is a cycle graph or not. Don't worry about that. We didn't do LU decomposition directly. Another AVL tree, insert the next elements. We've got this tree. Go ahead and insert from there. 2-3 tree, we start with a tree, and here's a bunch of more elements. Go ahead and insert them. And then some other heap questions over there. So, what's the muddiest point here? Which one do you want to look at next? Or any of them? Knapsack. Yeah, there was the knapsack. Okay. Recall the following decision version of the 0-1 knapsack. In other words, you're just asking a question, a yes or no question. It's kind of like a Boolean function. Given a set of items that when weights and integer values, a capacity W, and another parameter V, we want to output yes if there exists a feasible solution with a total value of V and no otherwise. Suppose that we have an algorithm A that solves this problem. It outputs yes or no, right? In other words, given the things that we need, say A, W, or the items, I guess, now we're going to get confused here because I'm calling it A. The weights, the values, and this parameter V here, it outputs yes if there is a feasible solution, that is some subset of the values whose weight, the sum of the weights does not exceed the capacity. I forget what we use, yeah, weight capacity here. And no, a feasible solution of total value V, right? No otherwise. Okay, and suppose that this runs in order n squared time, right? And you'll see that you can kind of do that, but it's called, what is it called? It's called pseudo-polynomial time, right? When we look at dynamic programming after graph algorithms after the midterm, you'll see a kind of a solution that looks like this, right? Design an algorithm that uses A as a subroutine that finds the value of the optimal solution. Remember, what are we trying to do here? We're trying to optimize our value. We're trying to steal stuff that we can put into our knapsack. We can't fit too much into our knapsack, so we can't steal everything. So what do we steal? We can either steal something or not steal something. 0-1. You can take it or you can leave it. I want to maximize my value, right? So what kind of questions should I start asking? Suppose that the total value of all items is $100. What's the first question I should ask? Is there a feasible solution that's worth $100? No? Okay. Is there a feasible solution that's worth $99? No? Is there a feasible solution that's worth $98? ... Until you get down to an answer of yes. If I start at the very top and I work my way down, then I find the best solution, don't I? So, what is the absolute best possible solution? I'll call it max, and it's simply going to be the summation of I running from 1 up to n of all values v sub I. Right? That's the best that you could hope for. So for, I'll go ahead and go with k, running from max down to 0, say, because there might not be any feasible solutions at all, right? If your capacity is so low, you can't steal anything. Right? Well, we'll ask this question. A, W, vals, and instead of this V parameter, K. If it answers yes or true, then output k. That's the best possible solution, the value of the best possible solution. Right? And certainly it's going to answer 0. Right? So you don't need anything after this to take care of the other case. It could say that, well, there's no feasible solution, so the best possible solution is going to be worth 0. Don't steal anything. Right? Be a good person. Don't steal anything. Right? So this right here is order n squared. Well, this is going to be order what? Max of the value. So it could be order as it's unbounded. This is why it's pseudo polynomial time. But we'll just say that it's n, right? Because there are n of these things here. Right? So take the maximum valued object and then say that it's worth $100. Well, then certainly the sum of all of these is at most 100n. And so you could say that it's order n because 100 disappears with asymptotic analysis. Right? Okay? And so altogether, this is going to be order n cubed. What we were actually doing here is we were transforming a decision version to what's called an optimization version. You can ask a question: does there exist a solution with this value? Yes or no, right? It's not giving you any information. What is that solution then? That doesn't tell you what the best solution is. But oftentimes you can use a solution to a decision version to solve an optimization version, finding the value of the best solution. And finally, you can transform it into what's called a functional version, where I'm not interested in yes or no questions. I'm not interested in value questions. I'm interested in give me the actual best solution. Tell me which items I should actually steal. Right? Decision version, yes or no. Optimization version is just a number. And functional version, give me the actual subset. Right? So could A be used to find the actual optimal solution? Give some reasoning for your answer. We were very loose on that. That was why it was only worth 5 points. It's not too apparent at all. You'd basically still have to find the subset that sums to that value, and that in itself is also an NP-complete problem. Right? So it's one that I covered in that semester 2 years ago. It's not one that I covered in this semester. That's why I rewrite my exams every time, because I don't cover everything exactly the same way every summer. Right? You want to go back to anything else, or just keep going linear order here? Okay. A brute force algorithm is implemented to find the optimal solution to the satisfiability instance. When it runs, it can examine 18 quadrillion, that is 18 times 10 to the 15 assignments each second. For a formula with n equals 75 variables, give a worst case estimate on how long the algorithm will run. Well, how many possible truth assignments are there in satisfiability? 2 to the n. Because if you have n variables, it can be true or false, 2 times 2 times 2, n times. That's the number of possible assignments. Your computer can find 18 times 10 to the 15 per second. 18 times 10 to the 15 per second. This gives you, this is assignments per second. This gives you the number of seconds. If you want to, in the denominator, you can go ahead and modify this so that there are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365.25 days in a year. This gives you the value in years. All right? And then you can pull out your calculator and find out what that is. It's still going to be astronomical. Okay? Again, open book, open computer, open Wolfram Alpha. A. B. Let T be a 2-3 tree with 1,359 keys. Give an upper and lower bound on the height of T. So again, open book, open note, open computer. What was n basically is the number of keys, 1359. Do you remember the lower bound and the upper bound with respect to n? For the, I think it's the upper bound is going to be log base 2 of n minus 1 plus 1 n plus 1, I think, minus 1. Right? This is the upper bound. Sorry. I'll put a question mark here because, again, I don't remember what it was. We derived it in class. And then the lower bound is going to be something like log base 3 of n blah, 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 blah. Right? When you plug in n, you get estimates on all these things. Again, it's just plug and chug. Remember your notes. See. If anybody wants, has those readily available, then we can do it right now. Let A and B be 256 by 256. In other words, n is 256 matrices. Using Strawson's algorithm, about how many multiplications are made to multiply them? About how many additions? So if I've got n here, and I remember that Strawson's is about n to the 2 point, what was it? 2 point blah, 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 blah. Then all I need to do is compute 256 to the 2 point blah, 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 and I get my answer. Pull out your calculators. Right? D. Consider the following hypothetical, again, I don't have a calculator readily available, and I don't remember what the exponents are here, but that's why it's not closed book. It's not like the one that I hated from calc all the time was what's the derivative of sine, what's the derivative of cosine. I could never remember which one had the negation. You could always flip them, but I never remembered which one had the negation. So I think inconspicuously I put S and then minus and C and plus or something, whichever one, but I forget what it was. That's why I hate closed book notes, or I hate memorization tests. Consider the following hypothetical algorithm that uses a divide and conquer algorithm to solve the closest pair problem. It does so by dividing a set into 4 subsets of equal size and performs a linear amount of work to determine the closest pair of points that lie on any 2 sets. Give a recurrence and determine the efficiency of this supposed approach. So if I have C sub n being my number of comparisons, and I've got 4 subsets, that means I need to make 4 recursive calls. Each subset is 1/4 the size of equal, because they're of equal size. And then I do a linear amount of work to combine all the solutions back. Again, this is just master theorem. A, B, C, and D, or A, B, and D. A is 4, B is 4, and D is 1 in this case because it's a linear amount of work. 4 versus 4 to the 1, well, guess what? They're equal. So by case 2, we have that this is going to, C sub n is going to be n to the d, but that's 1, so it goes away, log n. Is that any better than the solution that we looked at? Nope. It's exactly the same asymptotically. So it doesn't matter if you split it into 2 sets or if you split it into 4 sets. Right? I'm sure that you could do the same trick of only looking at the 6 nearest points or bounding it so that you're only looking at a certain number of points. Because it's Euclidean, right? It doesn't matter if you cut it in half by an a y factor or an x factor or both, right? You could actually do this, but it doesn't buy you anything because it's the same asymptotically. A cycle graph, Cn, is a graph on n vertices that forms a cycle of length n. Right? So in other words, for example, this is say 235 material. Here's C3. It's just a triangle. What does C4 look like? It's a cycle of length 4. C5 looks like it's just a pentagon, right? Et cetera, et cetera. Design an algorithm, give good pseudocode that, given a graph G, determines if it is a cycle graph or not. Analyze your algorithm. Right? So how could I do this? I could take a walk, start at an arbitrary vertex. First of all, is that going to be a cycle graph? Nope. So what could I check locally, first of all? That the degree is 2. Okay? Well, if the degree is 2, then move on. Go to the next one. Is the degree 2 there? Yeah? Well, okay, then go to the next one. Maybe you want to keep a previous and a current, so that when you go to the next one, it's the one that's not the previous. Right? You look at the neighborhood without the previous, and that's the one that you go to. Okay? Keep doing that. If you ever find, say, a dead end, what if it was like that? Right? Well, I came here, now the degree is 1. I'm at a dead end. Is that going to be a cycle graph? Nope. If I find something of degree 2, is that going to be a cycle, or degree greater than 2? Is that going to be a cycle graph? No. So keep doing that until eventually you get back to where you started. If you get back to where you started, does that automatically mean that it's a cycle graph? Careful. Is that a cycle graph? Nope. 1, 2, 3. But there are 4 vertices, so not a cycle graph. Right? That's the basic idea. Okay? Here's my input, a graph G. If you wanted to get away with this, you could say a connected graph G. And then you say, oh, okay, well, I know I'll solve that other problem later on. A graph G equals V comma E, and output is going to be true if G is Cn, where n is, of course, the size of the vertex set. False otherwise. Okay? Well, we could, make some basic checks. For example, we could check how many edges there are. That might be a way to get around that. To get around that, 1, 2, 3, but there are 4. If it were a cycle graph, there would have to be 4, right? But that doesn't get you around every single possibility. Is that a cycle graph? Nope. Even though it's 1, 2, 3, 1, 2, 3, there are 6 vertices, 6 edges. So that by itself is not a disqualifier, right? So be careful. You can always I love these kind of things because it can come in 235 because I can come up with counterexamples. I prefer giving questions of the form prove or disprove, where the disproof is simply thinking about it and then coming up with a counterexample. It forces you to understand the definition, right? And then it's a really easy solution because all you have to do is draw a picture and that's it, right? And explain why this is a counterexample, right? All right, so let's go ahead and start with the current previous. Like we said, we'll go ahead and keep track of the current and the previous. On arbitrary vertex in V. Again, it doesn't matter where you start. Okay? You could check up front, does everything have a degree 2? I'll just check those on the fly. So while, and then we can come back and fill that in. When do I stop? I'm going to, first of all, I'm going to check if the degree of the current vertex is not equal to 2. Coding, that's not even Python code. Not equal. There we go. That's more pseudocodey. Right? Output, false, because you're immediately done. Okay? Otherwise, you know that the degree is 2. We need to now determine what we're going to do to go to the next vertex. So I'll go ahead and create next. It's going to be the thing in the neighborhood of the current without the previous, because we don't want to go back to something that we've already visited. Okay? By the way, there are lots of solutions right? You could color the vertices, which is what we're eventually going to do with DFS. You could say, here's another way that you could do it. If it were a cycle graph, you could cut out one of the edges, start at the other endpoint, and then verify that it's a tree, right? And then that means you don't have to make a check of did you get back to the one that you started with. There are lots of variations that you can do on this. But otherwise, this is the one that I'm just thinking of, right? The next one will be the next one. So I've gone on to the next one. This is my next now. So I need to update the previous. Previous. I need to update that to current. I need the update to the current to the next. And then go on to the next iteration. But you also need to keep track here. If I start here, go 1, 2, 3, 4, I'm stopping, then I need to answer yes. So I'll have a counter here, count. I'll initialize it to something. I should have left myself some more room. And I'll increment it down here, count plus plus. Okay? There. My condition at the end will be if the count, depends on where I started too. So now we need to know where I started. So if I start here and then I count 1, 2, 3, 4, I'm counting the number of edges. So if the count is equal to n, then I'll output true. Else output false. Okay? There. If it's 1, 2, 3, then I missed something, right? While. Now, what's my condition for continuing? When do I stop? 1, 2, 3. I could use this as I could use the counter here, and when I get to n, I could break out of this while loop. But that's not going to help because I could get stuck into a cycle and go 1, 2, 3, or say 1, 2, 3, 1, 2, 3, and then now it's 6 that I've counted. But that's not a cycle graph right there. I need to make sure that I get back to where I started. Okay. So maybe I need another, or I'll start my count. Sorry, at 0. I should have said that. We could have a start vertex. Oops, put it down here. Start will be current. And that way, while current is, what do I want? Current is not equal to start. It will be, I need to get this so I could do a do while loop instead. I could say previous. While previous is not equal to start. But now I'm going to be off by 1, aren't I? So that's all right. Just go +1 over here. There. So you see why I was off by 1 here? I have to get this while loop to execute at least once. So you could write a do while loop instead. But if start and is equal to current, then this will never execute. And so I needed a different condition here. While previous is not equal to start. That way that this is start. I go around, right? This becomes my previous, and I've gone on to the next vertex. Gone on to the next vertex. That's when I stop. Right? Initially, previous is nothing, so this will execute at least once. Right? Again, lots of variations here. You just need to come up with one. Okay. Again, ignore that. More AVL trees. Consider the AVL tree in figure 2. Insert the elements into this tree and draw any resulting configurations after the insertion along with any type of rotation that occurs. Where will 15 get inserted? Less, 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 greater. So 15. And so I've got an unbalance to the left, then to the right. So I'll do a right, left rotation. And what do I end up with? Left, right, so 15, then 10, then 20. So that's done. 105 gets inserted as right child of 100, and then I would end up doing a left rotation here. So 30, 100, 100, 50, 105. This is unchanged, 15, 20, and 10. 25 would get inserted over here. It would not affect it adversely enough to cause any rotations. 65 would get inserted right here. Again, it's not going to cause any other rotations. 35 is greater than 30, less, less. So 35, again, no rotations. All right. Two, three tree. Insert the following elements into this tree. I don't know. Yeah, I think you can end up with this tree. In fact, is this the tree that we ended up with? Something like it. All right. Let's go with 15. 15 is less, so it ends up getting inserted as a companion to 10. 30 and 100. 105, there's plenty of room here, so 30, 20, 50, 100, and 105, 30, 10, and 15. 25, again, there's plenty of room here, so this becomes 25 and 30. And now it's completely full, so we're definitely going to have to split it up and promote something when 65 comes in here. 65 temporarily gets inserted here. It gets promoted up, which looks something like 20, 50, 65. Oh, sorry, what? 100. 100, thank you. 100 gets promoted. 65 is over here. 100 gets promoted up. And temporarily, we have these four children, 10, 15, 25, and 30, and 65 and 105. Oh, which gets split, sorry. So we've got these four children temporarily. 50 gets promoted up, becoming the new root. 20, 100, 65, 105, and then these have three nodes, 25 and 30, and 10 and 15. That was 65. 35 is less, greater, so what happens here? This is 25, 30, and 35. So 30 gets promoted up, but there's there's room for it to be up here. Right? This becomes then 50, and it stops the promotion basically. 20 and 30, 100, 65, 105. And the 25, 35, and this gets split to be the three children, 25 and 35. There. So a variety of 2 nodes, 3 nodes, but they're all at the same level because you always insert as a leaf. Right? I don't know if that will be bonus or not, but if there are, then yay. Usually it's, I'll make like a dozen questions, cut them down to 8, and then if it's still too long, I'll just make one of them bonus or something. Right? Insert the following keys into an initially empty min heap and indicate the total number of swaps required. So this is 156 material essentially. I don't know why I made it bonus 2 years ago, but I did. So 10 gets inserted. 90 gets inserted as in the next available spot, but it's a min heap, so it's okay. 5 then gets inserted, and but it breaks the min heap property. These get swapped. So there's one swap. 5, 10, and 90. 50 gets inserted, and ends up being swapped just once. So 5, 50, 90, and 10. 30 gets inserted right here, right? And it ends up being swapped once. So counting these up, 2, 3. And we end up with 5, 10, 30, 50, and 90. Next is 15. That gets inserted over here. Does it get swapped at all? Nope, because it's greater than its parent. 2 gets inserted over here. What ends up happening is these get swapped, and then these get swapped. So 3, 4, and 5. And we end up with 2, 5, 10. 15 is unchanged. 30, 90, and 50. 3 gets inserted over here. How many swaps are going to happen here? There's 6, 7, and that's where it ends up because it's not greater than 2. So we have 2, 3, 30, 90. Here we go. And then everything else, what was it? Off of 3, we've got 50. 5, 15, and 10. Okay. Then the last one we insert is 1. How many swaps is that going to result in? 1. So our count was at 7, 8, 9, 10. So 10 total swaps. And the final configuration of this thing is going to be 5, 15, and 10 are unchanged. This swapped all the way up, so all these things get swapped all the way down. What was up there? 3? 90, and then 30 is down here. There. So 10 total swaps. The last one is, suppose we wish to insert a contiguous sequence of integer keys. I plus 1, I plus 2, ... all the way up to n, into an initially empty min heap. What order should we insert them to minimize the number of key swaps? So for example, it could be like 7, 8, 9, 10, 11. What would be the best order? How many permutations are there of 5 things? 5 factorial. What would be the best order to minimize the number of keys? The key swaps, I should say. Right there, that order, right? Why? Because if you're always inserting the next largest value, then you will never swap it with its parent because you already put in the smallest value, right? You'd end up putting 7, 8, 9, 10, 11, right? Do you ever make a swap? Nope. Right? So, in order, right? There are, of course, other answers. You don't have to go in absolute order. You can go, you can, anything that ends up with a tree that, its children get swapped a little bit, as long as it has a fullness property. So for example, 7, 9, 8, 10, 11 would work. 7, 9, 8, 11, 10 would work, right? But you'd have to, this is so general here that the simplest and best answer is just put them in order. That's it. In fact, I don't think that that's what the Python implementation does. But one thing that you can do to heapify initially is to simply pay for the sorting up front and then put that into an array, and there's your initial heap. All right, 2 years of midterms. I could have printed out 2016 if you wanted, but I didn't. And we don't have that much time. Any last questions, homework or otherwise? And I will post this so that you can get the benefit as a video. But they should be. I put them there just now. Not the graph stuff from Friday, but I could put that up there if you wanted tomorrow. I don't always have 100% control over that, I trim off the beginning and the end, and then like one day last week it took like 9 hours to get it back. But usually it's fast enough, but I will do it as soon as I get home.